In this video, we're going to talk about another type of sequence that's special, that's called a geometric sequence. So again, we start with the definition. So a geometric sequence is, again, a sequence that can be defined recursively as, so A1 is some value A, and then to get to AN, you take AN minus 1, but you multiply by some constant R. Okay. Actually, sorry, I wanted to define it a different way. So if you divide two consecutive terms, so AN divided by AN minus 1, you get some constant R. Okay, so so the other way to define it, as I wrote previously, so this is the more common way. So A1 is A, and AN is R times AN minus 1. Okay, so this is the way we normally think about it defined. Okay, but the reason why the first way is because where R is a constant, so we call R the common ratio. So if I take the ratio of two consecutive terms, I get some constant R, which is the common ratio. Okay, and that happens when each term, you get to the next term by multiplying by this common ratio. Okay, so an example, so if 10 and 9 are the first two terms, so that means that A1 is 10 and A2 is 9, are two terms of a geometric sequence. Okay, so we know it's geometric, so that means we know that AN is R times AN minus 1, or AN over AN minus 1 is R. Then we can find the next two terms. Okay, so R we could find by taking A2 over A1. So that's 9 over 10. Okay, so R is 9 over 10. And we know A1 and A2, we want the next two terms. So that means that A3 is going to be 9 over 10 times A2. So that's 9 over 10 times 9. So that's going to be 81 over 10. Okay, and A4 is going to be 9 over 10 times A3. So 9 over 10 times 81 over 10, which is going to be 729 over 100. Okay, so those would be the next two terms in that sequence. Now, like we did with the arithmetic sequences, to show that a given sequence is geometric, we need to show that the ratio of any two consecutive terms is a constant. Okay, so that means we want to take AN over AN minus 1, and we want to show that it's a constant. Okay, so if we look at this sequence, Sn is 2 to the n, and I want to know, is this geometric? What I'm going to do is I'm going to take Sn and divide by Sn minus 1. So that's 2 to the minus n over 2 to the minus n minus 1. Okay, so now I have the same base dividing. So what I can do is subtract the powers. So this is 2 to the minus n minus negative n minus 1, which is 2 to the minus n plus n minus 1. Okay, so then the n, I have minus n plus n, those are going to cancel. So I get 2 to the minus 1, or 1/2. Okay, now this is a constant. Okay, so that's going to be my common ratio, R. Okay, so because that's a constant, the sequence of SNs is a geometric sequence. Okay, now if something is not a geometric sequence, all you have to show is that the pattern doesn't maintain. Okay, so if you try and show that it's geometric, taking this, and you get something that you can't simplify, or that you don't know what to do, you might want to think, okay, what is S1 and what is S2 and what is S3? Do I multiply by the same thing to get from one term to the next? Okay, so just keep that in mind. I'm going to leave example 3 for you. So remember, it doesn't say show Tn the sequence is geometric. It says, is this sequence geometric? Okay, so the answer might be no. Okay, so just keep that in mind when you're trying to do that one. Now, if you do have a geometric sequence with common ratio r, then you know that A2 is A1 times r. Okay, but then A3 is A2 times r, but A2, okay, is actually A1 times r. So then I could write A3 as A1 times r squared. Similarly, A4 is A3 times r, but A3 is A1 times r squared. So A4 could be written as A1 times r cubed. So now you might see the pattern. So the 3, it's always A1 times r to some power, and the A3 is power 2, A4 is power 3, so AN is going to be power n minus 1. Okay, again, I'm just going to put this in a colored box so that we know it's important. Okay, so that's the formula for the nth term in a geometric sequence with common ratio r and first term A1. Okay, so using that, let's find the nth term of a geometric sequence with A1 is -2 and r is 4. Okay, so we just use that formula. So AN is going to be A1, so -2, multiplied by r, the 4, to the n minus 1. Okay, so that's the formula for the nth term. Okay, now I'm going to leave these two examples for you to try. So you want to find the 8th term, and then you also want to find the nth term similar to what we just did there. Okay, now be careful. This one gives you A2, A2, not A1. So here they gave me A1. So you want to be careful. It's not exactly the same. Okay, so like again we did with arithmetic sequences, we often want to add up geometric sequences. So what we did for the arithmetic sequences is also known as a partial sum. So it's the sum from the first term to the nth term. So that's not the entire sequence, okay? That's only the first part of it. So we call that a partial sum. Okay, so if Sn is the sum of the first n terms, that means that Sn, so I could rewrite these terms. So this is A1, A2 is A1 times r, A3 is A1 times r squared, and An is A1 times r to the n minus 1. Okay, now this you could actually rewrite, so I could factor out the A1. And then I'm going to have 1 plus r squared all the way up to n minus 1. So this is A1 times the sum from k equals 1 to n minus 1. Or I could do actually 1 to n. And then it's going to be r to the k minus 1 power. Okay, so then the 1 here is r to the 0 minus 1. Sorry, 1 minus 1, but it's r to the 0. Okay, so that gives you 1. So this is 2 minus r here. This is r to the 2 minus 1, r to the 3 minus 1, etc. Now this sum is actually equal, so this is not one of the formulas that we know, okay, but this one is actually equal to 1 minus r to the n over 1 minus r, okay, as long as r is not 0 or 1. Okay, then it would be equal to that. So this is, let's just get rid of this. So this is the partial sum. So the first n terms. Okay, so this is as long as r does not equal 0 or 1. Okay, so let's do an example. So if I want the sum of the first 18 terms of this sequence, so it gives me a1, and then it gives me the formula for an. So that means that, now it doesn't tell me that it's geometric, so maybe I should check. Okay, so an over an minus 1 oh, I don't need to do this because the formula is exactly, this is a geometric sequence because it's a number times the one before. Okay, so this is defined geometrically. Okay, and the r is 1.1. Okay, that's what we multiply each term by. So that means that we're trying to find S18. Okay, so it's going to be A1, which is 2, times 1 minus 1.1 to the 18 over 1 minus 1.1. And if you compute that, you get 91.198 as your sum. Okay, now I'm going to leave these next two for you to do. Okay, now this one, so this number 8 is very similar. Okay, number 9 looks a bit different. Okay, but this inner bit here is a geometric sum. Okay, a geometric sequence. So you're summing up the terms of a geometric sequence. Okay, so it is actually the same thing. Now, for geometric sequences, we can actually sometimes talk about the infinite sum. Okay, so that's the sum of the entire sequence. So that means that your n is actually going to infinity. Okay, now, if your r, your ratio, is bigger than 1, so in absolute value, so it's so what that means is that you're less than -1 or you're bigger than 1. Okay, then this, you're always multiplying by something that's bigger than 1 or bigger than -1. So what happens is we say that this sum, the infinite sum, diverges. Okay, so i.e. it approaches either plus or infinity or minus infinity. Okay, so it doesn't approach a nice number. Okay, so it means that the sum just keeps getting bigger, bigger, and bigger, or smaller, smaller, smaller. Okay, so you just keep subtracting numbers or you keep adding the numbers. Okay, but if your ratio is between 0 and 1, so maybe I should write i.e. Your r is between 1 and -1, so not an absolute value, then it does converge. Okay, so then the sum is actually equal to your first term over 1 minus r. Okay, so it actually converges to this number. Okay, so the sum, I should say. The sum converges to this number. Okay, so we can actually compute what the infinite sum approaches. So I'm going to do one example and then leave the other one for you to try. Okay, so the sum of all the terms in the geometric sequence 4 over 3 to the n. Okay, now 4 over 3 to the n I could write as 4 times 1 over 3 to the n. And then that would be 4 times 1 over 3 to the power n. But my geometric sequence, the powers are n minus 1. So what I could do is 4 times 1/3 times 1/3 to the n minus 1. So I can take out one of them. So that means that it's 4/3 times 1 over 3 to the n minus 1. You don't have to do this, okay? But this is a way to show that A1 is 4/3 and the R is 1/3. Okay, or you can just plug in n equals 1. So that means that A1 is 4/3, and then the R is going to be A2 over A1, and A2 is 4 over 9. So then I would flip the bottom one and multiply, and you get 1/3. Okay, either way, it doesn't matter. So you can rewrite it this fancy way, and then you can see what the A1 and the R are, or you can just compute it this way. Either way, the infinite sum, so we normally call that S. Okay, so that's the sum from k equals 1 to infinity of 4 over 3 to the k. Okay, that's going to be the first term, so 4/3 over 1 minus 1/3. So that's 4/3 over 2/3, which is 4 over 3 times 3 over 2. So that's 4 over 2, or 2. So this sum, actually, if you add up all the terms, approaches the number 2. Okay, so it's going to be 4/3 plus 4/9 plus 4 over 27, etc., etc., etc. Keep adding all those terms up, so you never stop. It only approaches the number 2. Okay, so I want you to try that similar for number 11. Again, this is the same because this thing in here is a geometric sequence, and I guess I should have said here, so this R is less than 1. So that means that the sum converges. Okay, so it in absolute value, I guess, okay, is less than 1. So you want to try the same thing down here. Okay, the R is going to be in the same category, so this sum will converge, and you want to find what it converges to. Okay, so that's an introduction to geometric sequences.